Today we are going to talk about MRI and how it works. And there's a few reasons why MRI occupies so many chapters in the book. The primary reason is that it is a very powerful and widely used technique in cognitive neuroscience. And so there are a lot of different applications, so you're probably familiar with fMRI. And then there's also structural MRI and diffusion tensor imaging. But understanding how any of these techniques work and what their limitations are is fundamentally dependent on understanding how the technique itself works. And the technique itself is somewhat more complicated. I mean, they're all complicated if you delve deep enough into the physics, but to even understand like how you get the signal out of an MRI scanner is fairly complicated. So there's a whole chapter in today's lecture just on MRI signal generation before we ever get to the fMRI or the applications, which is unlike the other topics in the book, but both because I think it's more complicated to try and understand, and because understanding is so fundamental to understanding such a broad majority, really, of cognitive neuroscience research. It's worth going into in detail, even if sometimes it makes your head want to explode. So that's what an MRI scanner looks like. It's a big plastic donut, and critically inside that scanner, so we would call, it's not quite oriented right. So we would call that the bore of the scanner, where the subject lies. So the subject would lie on this bed, or the patient. For a head MR, they'd have their head inside that bore, that tube. And the main part of what's around them is a very strong magnet. And as I mentioned before, these are sort of 1.5, 3 Tesla, 7 Tesla, even a 1.5, which is sort of the weak end of the weaker end of MRI scanners for clinical use. The magnetic field there is strong enough to pull any sort of metal out of your hand from 20 feet away, send it flying through the air and into the scanner, and that so there's safety risks associated with that, and also it just sort of demonstrates how powerful a magnet is, and that's critical to getting good quality images. And as we'll probably touch on a little bit, but the difference between the field strengths of 1.5 to 3 Tesla to 7 Tesla really comes down to the quality of the image that you get. And so once I get to contrast generation today, we'll talk a little bit more about this, but basically we're trying to maximize the contrast or the difference in signal between different tissue types. And the stronger the magnetic field, the more you can separate the signal from those different tissue types. And that, so ultimately it sort of gives you better signal to noise, or what we call contrast to noise in the image. And both for functional imaging and for structural imaging, that improved contrast to noise buys you a number of things, including obviously sort of better image quality, but that means that you can push the spatial resolution higher. Typically, sometimes you can scan a little faster. The 7 Tesla scanners, so the highest field ones, they're being used for functional MRI, but probably the more popular application is actually for diffusion imaging, which is where you're measuring white matter tracts, because it allows you to get higher resolution images. And the 7 Tesla seems to be necessary to get the level of resolution that we really need to resolve human white matter tracts. So main part is that magnetic field, and that magnetic field is always on. And then on top of that, there's radio frequency coils in there that send radio frequency energy. Talk about that later, and also gradient coils that are able to adjust the strength of the magnetic field in different dimensions. So there's one magnetic field that's always on, and that's whatever is the sort of sticker field strength of the magnet. But then there's these other radio waves and gradient fields, and all of that hardware is encased inside that donut there. So from a safety perspective, again, the magnet's always on. MRI scanners are always in a shielded room, which helps in both ways. It doesn't shield against the magnetic field per se. In fact, what they do is they design the scanner and figure out how that magnetic field drops off with distance and define what they call like a 5 Gauss line, Gauss being a sort of measure of magnetic field strength at a much weaker level. And the walls of the MRI scanner room are typically on or past that 5 Gauss line, meaning that you've basically created physical walls around the scanner that keep the dangerous magnetic field inside that room. and then you control access to the room as a means of safety. The room's also a big Faraday cage. It's shielded against radio frequency energy because we're using that in the scanning process, and outside things like actual radio waves, TV waves, cell phones, and so on would actually get picked up by the MRI scanner and cause artifacts, so it's shielding against that. But it's not shielding against the magnetic field. That's all around sort of physical containment of the room. All right. And this is an interesting historical note. So there was a Nobel Prize that was handed out for the discovery and development of magnetic resonance imaging, which went to, as you can see here, Peter Lauterbur of the University of Illinois Urbana-Champaign and Peter Mansfield of the University of Nottingham. So that was a 2003 Nobel Prize in Physiology or Medicine. There was actually another guy, Raymond Damadian, out of New York, who has claimed that he invented MRI and did a lot of early work in the 70s around this, and for various reasons was not included in the Nobel Prize and was very publicly upset about that. This article, which was in Nature, was I thought kind of interesting because it describes a guy, Vladislav Ivanov, who was lieutenant in the Red Army in the Soviet Union, who actually invented the MRI in 1960. So I think he was posted in St. Petersburg. I thought he was in Siberia. Doesn't so much matter. Anyway, yeah. So he actually submitted a report, and this is the days of the communist government in the Soviet Union. Submitted his report up the chain, and basically his superiors didn't understand it. So he included a diagram and lots of details. They thought about it, they couldn't figure it out, so they sent it to a critic who came out sarcastically against it, who sent it to his boss, who signed off on it. And in fact, after that, they started to spy on him and this sort of thing, so he was never able to actually develop his idea, although he actually built one. So, a good 10 years before anybody else was doing it, he was doing it, but sort of an interesting sort of history of science side note there. Anyway. So protons are the fundamental building blocks of water molecules, and they're the thing that all human MRI really relies on. There are actually a number of different atomic nuclei that could be used for MRI, and that are used in chemistry. So in chemistry, they call it nuclear magnetic resonance, or NMR. MRI is basically an expansion of NMR to use it for human imaging. So in chemistry, you use NMR mostly on test tubes or very small samples. There you can have even much higher field strengths, and you can actually tune them to different atoms and not just hydrogen. But in human imaging, we focus exclusively on hydrogen, mostly because it would be a lot more expensive to build the MRI scanners around multiple different atoms, and because water is such a ubiquitous element in the human body. So when we look at a hydrogen atom, it has, which we also call a proton. Protons are subatomic units, but a hydrogen atom is a single proton, so it's sort of interchangeably called a hydrogen atom or a proton. So we've got a proton, which can represent as a sphere, and it has a spin around an axis. So you can think of it as a dipole, because its axis has an orientation, and it spins around that. And these axes are actually like magnetic poles, right? So the Earth has a north pole and a south pole. Our compass points to the north pole. So the arrow here is essentially the north pole of that proton. And just like a compass, if you hold a magnet near the compass, you can pull the north needle around. When you put protons inside a strong magnetic field, they have a tendency to align with that magnetic field. So here in the top panel, you can see protons with random alignments, so they're not in a magnetic field. And over here on the right, we're representing what we call the net magnetic vector, or net magnetization vector, which is basically sort of if you sum up the orientations of all the protons, what do you get? In this case, we get 0 because there's equal numbers pointing in every direction. And it's important to realize this is a 2D picture, right? But these can be oriented in 3 dimensions, really. Inside a strong magnetic field, the protons don't all sort of magically line up perfectly because there's a lot of other forces impinging on them. But a strong magnetic field like an MRI scanner, with a field that's always on, will have a weak tendency to pull these protons into alignment. And the stronger the magnetic field, so the stronger the scanner, the stronger that tendency is. So that's part of where having a 3 Tesla or a 7 Tesla MRI is better than a 1.5, is it's pulling more of these protons into alignment with it. And as a result, our net magnetization vector now has an orientation that's parallel to the magnetic field. In other words, on average, the orientations of these protons are aligned with the magnetic field. So if you're lying in an MRI scanner, you imagine you're flat on your back with your head sort of sticking into this thing. The magnetic field is pointing towards the top of your head, basically. So it's sort of aligned in a line, like an arrow going through that bore of the scanner. So you can imagine it that way. All right, so that's the first thing, is we have the strong magnetic field. As soon as we put a person's body in there, the protons line up kind of weakly with that. Now, it's not just alignment. It turns out that protons exhibit another property, which is precession. So I already mentioned they spin, right, which is the blue arrow there. But they also, their axis actually wobbles. So it doesn't perfectly align with that strong magnetic field, but it's sort of rotating around it, kind of like a top, as a top loses momentum and it starts to fall over. These ones don't actually fall over, but they have this weird sort of wobble to them, which we call precession. And so you can see that precession represented there with the black dashed arrows. And so at the bottom here, over time, you can basically see how the orientation of that proton rotates or precesses around its axis, or in this case, around the strong external magnetic field. So they're kind of lining up with that, and they're precessing around it. And this precession is critical to MRI because it's sort of by leveraging the rate at which these protons precess that we're able to convey energy into the body and then read a signal out as energy, which is the MRI signal. And so it turns out that the frequency or the speed that these protons precess at is a fixed value, and it's a determined value. And it's determined by the Larmor equation, which is one of about 2 equations in this entire course. And it's basically saying this W symbol is precessional speed, and it's a function of the strength of the magnetic field plus gamma, which is a constant. It's called the gyromagnetic constant. And it's a fixed value for any atom. And so for hydrogen, we know that the gyromagnetic constant is 42.57 megahertz per Tesla. And we know the strength of our magnetic field because we know we have a 1.5 Tesla scanner, say. And so for a 1.5 Tesla scanner, you just multiply 1.5 times this 42.57, and it tells us that our protons are precessing in that scanner at 63.9 megahertz, which is really fast, and that's in the radio frequency range. So we know that all of the protons are effectively precessing at this rate when they're inside the scanner. And as I say, we can leverage that through a physical phenomenon known as resonance. So if you have any sort of experience, especially with string musical instruments, but maybe in other contexts as well, or even with this 2 tuning fork demonstration here, when you produce sound, the reason we hear sound is that it's sound waves. Sound waves are traveling through the air. Now, these are much lower frequency than the kind of radio frequency waves we're talking about here. But nevertheless, those sound waves move through the air. And when they hit your ear, the reason you hear sound is because your eardrum is vibrating, which means it's resonating. So that sound wave is transferring energy to your eardrum, which causes it to vibrate, which causes all kinds of other stuff. Similarly, if you have something like a guitar or a stringed instrument and you play a noise in the room, you play a note on a piano, for example, if you're playing one of the notes that one of those strings on the guitar is tuned to, that string is going to start vibrating, and that's the resonance phenomenon. Is the string is tuned to a particular frequency and the sound waves are coming through, so they're transmitting that energy to the string. Only that one string is going to vibrate because only it is tuned to that frequency. So the resonance is specific to a particular frequency. So the same phenomenon basically occurs in MRI, that if we send in energy at this Larmor frequency, at the frequency that the protons are precessing in, we can they'll absorb that energy and basically use it in ways that we'll describe in a minute. Whereas if we send in energy at a different frequency, those protons won't absorb it because it's not at their resonant frequency. So you really have to sync up with the music. Another analogy I like to use is dancing, right? So if there's music playing, you dance to the beat. So you're syncing yourself to the beat of the music. And if you're not, then you're going to sort of stand out in a crowd because you're off the beat, kind of thing, right? So we've got these protons, they're precessing. We can send in energy. In this case, it's radio frequency energy because of the range that protons precess in. And that transfer of energy to the protons is called excitation. And what we're seeing here is sort of a visual geometric representation of the effects of excitation on the net magnetization vector. So remember, the net magnetization vector is the fact that your protons are sort of weakly aligning with the strong magnetic field. So they're all more or less aligned with that. So in these plots here, that's what we're calling the longitudinal plane, or B0. B0 is another term for the strong magnetic field. So that's the orientation of the net magnetization vector along the bore of the scanner before excitation. And then we can also define the transverse plane, which is basically 90 degrees away from that. So within the bore of the scanner, if you imagine me lying there, the transverse plane is sort of cutting through my midsection or something like that. All right. When we send in the RF pulse, the protons are absorbing energy, and that basically causes the net magnetization vector to flip or to move into the transverse plane. So in other words, they're absorbing energy, and they're able to sort of overcome the effects of the strong magnetic field, do their own thing, and specifically we're sending in the RF pulse along that transverse plane. So we're sort of pulling those protons that are at rest aligned with the B0 field, pulling them out of alignment, and sort of pulling them in the direction of the RF pulse. So they're absorbing energy that allows them to resist the strong magnetic field, move over. And the amount that net magnetization vector moves away from its original orientation with B0, we call the flip angle. So the flip angle is basically a measurement of the amount of energy that's put in, because the more energy you put in, the more you're able to push that vector away from alignment with that strong magnetic field. So you're sort of temporarily overcoming the effects of that strong magnetic field with the RF pulse. And so in one case in the middle here, we're showing a 45-degree flip angle, which basically means how much energy did it take to flip it 45 degrees. And then a stronger amount of energy, so a stronger RF pulse, can give us a 90-degree flip angle, anywhere in between. For a lot of MR imaging, it's the 90-degree flip angle that we're really focused on. And the reason we're focused on that is, so this is another slightly different representation. So here again, the orange arrow is B0, so that's the bore of the scanner. And then the transverse plane, there's kind of a gray disk going around it there. And the blue is the net magnetization vector, so all the protons in your body. So we've sent in our 90-degree RF pulse, which means we've flipped this net magnetization vector away from alignment with the strong magnetic field into this transverse plane 90 degrees away. And why that's critical is that the receiver coil, so the little antenna that's in the MRI machine that's reading out the signal that we're actually going to record, is in that transverse plane. So what that means is that you've got these protons, they're precessing. Every time that net magnetization vector crosses the receiver coil, it's going to induce a current through our good old friend, the right-hand rule. Right, so you've got these blue arrows, you can see they're sort of coming around. Every time they cross that receiver coil, they're going to induce a change in the current. And you can see the coil's a loop, so they're actually going to touch it, cross it twice in rapid succession. And because it's a loop and because right-hand rule, you're inducing a current, it means that you're going to induce a current going in one direction as it hits sort of the first side of the loop, and then in the opposite direction as it hits the other side of the loop. And that results in an oscillating signal. So the up is like when you hit the first one, and the down is when you hit the next one. And so the frequency of your oscillation is going to depend on how quickly this thing is precessing, which we already know because of our Larmor equation. All right, so basically what this means is when you're just lying in an MRI signal, MRI scanner, there's no signal to be recorded. But when you send in an RF pulse and you flip the net magnetization vector into the transverse plane, now it's crossing that receiver coil and it's going to generate a signal as long as it's flipped. The thing is, when you turn the RF coil off, it's going to revert back to its alignment with a strong magnetic field. So your signal generation is only going to occur while that RF pulse is on and slightly after, and then it's going to slowly sort of come back. And so we can describe, so a pulse sequence is basically the program that you write for an MRI scanner that tells it how to acquire an image. And the bare minimum pulse sequence, which wouldn't actually generate anything in practice, but the bare minimum you need is the RF pulse, which you see in there in red, and then the echo, which is the signal we read out, which occurs sometime later. So you send the RF pulse in, and then you start reading out from that receiver coil, and you get this oscillating signal. Okay. So there's actually a lot more that goes on when we flip that net magnetization vector. So yes, we're flipping it into the transverse plane. Now it's rotating and it's hitting the receiver coil. But the other thing that contributes to the strength of the signal that receiver coil reads is the amount of phase locking that's occurring. And so here, phase locking is basically, if you imagine in the simplest case, step back from protons for a sec, sine waves, like this one. So if we look at the red one as a reference waveform, I've drawn gray lines at the positive peak all the way along there. And then we've got other sine waves that are the same frequency, so the same sort of peak-to-peak distance. The orange one is what we call in phase, or phase-locked, meaning that the peaks line up with the red one. Whereas the green and the blue are out of phase, meaning their peaks don't line up with the peaks in the red one, the red being our reference. And the green one is a 90-degree phase shift, so it's sort of a quarter cycle off. And then the blue one is a 180-degree phase shift, meaning that when the red one is up, the blue one is down, basically. So phase locking basically means that the protons, so if you think of the protons precessing, we can imagine that the sine wave is just describing where they are in their precessional cycle. Right? So if I start over at the left here with this red one, you can imagine that's sort of, at one point in the transverse plane, and then as it's turning, it's just sort of doing that. And when it gets back up to a peak, so it goes down and then back up, that would be the same point within the circle. Each peak would be the same point in the circle. Okay. So when these protons are just sitting there and you're lying in the scanner, nothing else is going on, they're all precessing, but they're all precessing at slightly different rates because of other factors, just like the fact that they don't all align perfectly with the magnetic field. There's other factors that are sort of influencing things. So their precessions are all going at the same, more or less the same rate, but they're not in phase with each other. So as one's sort of here, another one's here, and they, going like that. What happens is when you send in the RF pulse, they all phase lock to that RF pulse. So you're sending in energy at exactly the speed that they're already oscillating, and you're basically pulling them all into alignment. If some sort of have to speed up or slow down to get there, they'll do that. So again, the music analogy is good there, right? So if I said, okay, everybody in this room just get up and dance. First of all, you wouldn't, because that would be super awkward. But if you indulged me, and there was no music playing, you'd all have to sort of internally come up with some music to dance to, and it probably wouldn't all be the same music. Whereas if I turned on some music and said, okay, everybody get up and dance, to the extent that you have any sort of inherent rhythm, you would more or less be bouncing to the beat of the music, right? And so that's where the phase locking comes in, is the RF pulse is like the music, and the protons are the dancers. And so they're all lining up with the beat of the music and precessing with that, as long as that music is playing. Again, so you're all standing up, you're dancing, because I'm playing the music, I stop the music. If you keep dancing, you're gradually going to sort of fall out of sync with each other, especially if you aren't looking at each other, because there's nothing to sort of align to. And so when we turn the RF pulse off, that's what happens to the protons, is they keep precessing, but they'll gradually sort of fall out of phase with each other because they don't have that strong external signal to synchronize to. And so that's basically the process that we do in MR imaging, is we turn the RF pulse on, pull these things out of the longitudinal plane into the transverse plane, and have them all phase lock together. And that phase locking is important for the signal that we record because if you look, so I'll come back to the other part, but if you look at this column that says T2 decay, when we have the RF pulse on, you basically have the net of all of the protons is sort of all together, right, because they're all synchronized. But over time, as they start going out of phase with each other, that's what you see in the sort of spread of the blue arrows, is now that's different protons are now precessing more and more out of phase. So over time, after you turn off that RF pulse, they'll go more and more out of phase with each other until they return to the basically purely random state, where all their phases are random. So really, when you do the RF excitation and then turn it off, there's two phenomena that occur when you turn it off, and they're related, but they're independent, more or less independent. You can think of them independently, and they contribute separately to the MRI signal. So the first one is T1 recovery, which is this return to longitudinal magnetization. So that's basically the return to alignment with the B0, the main magnetic field. And then the second one is T2 decay, which is this dephasing, which we talk about in the transverse plane specifically. So they're both sort of falling out of alignment with that transverse plane, but then they're also falling out of phase with each other. And it turns out that they're separate rates. So the rate that it recovers back into alignment with the strong magnetic field is separate from the rate at which the dephasing occurs, and different physical things affect the two of them. And so I'll come to what those factors are in a minute, but here we see the plots basically of how these things happen over time. So over on the left, T1 recovery, again, this is coming back into alignment with B0. You've got two lines here. One in yellow is for fat, and one in blue is for water. And so these two tissue types have very different speeds of T1 recovery. The fat, as you can see, is quite fast, so we've got time on the x-axis here. And water is quite slow. And we can quantify and come up with a number that we call the relaxation time of a particular material, whether it's fat, water, blood, bone, whatever, as its T1 relaxation time, which is basically how long does it take to get 63% of the way back to alignment, B0. And physicists know how to calculate these things. With T2 decay, it's the same idea, except it's going the opposite direction because this is sort of the transverse magnetization. So in the transverse plane, how much signal do you have? And so that is large when you first turn the RF pulse off, and as it recovers, it goes out of phase, that goes down. The one thing I didn't explicitly say yet that I meant to was that, remember, the receiver coil is in that transverse plane. And so when we get that phase synchronization of all of the precessions together, then you've got one thing that's rotating around or precessing around at our Larmor frequency, and it's hitting the receiver coil, and all of those protons are basically hitting that receiver coil at the same time, so it's going to be a big signal. As they fall out of phase, what that means is some of the protons are going to hit that receiver coil early, some are going to hit it late, and so you're going to get a reduction in the strength of the signal that you're seeing in that coil because of that dephasing, and that's going to sort of mush the signal up quite a bit. And so your signal goes down there. And again, the T2 decay time for fat is much faster than the T2 decay time for water. And there's a couple of reasons for that, and basically it has to do with the fact that you're sending energy in to these protons, they're absorbing it. And so both of these phenomena have to do with how quickly those protons lose the energy. And the way they lose the energy is transferring it to other things around them in what we call the molecular lattice. And so that the fat has faster recovery and decay times because fat tends to be quite densely packed. There's hydrogen protons in it, but lots of other kinds of atoms as well that aren't necessarily absorbing the RF energy directly because that's tuned to the protons. But once the protons have it, they can sort of release it to this matrix around them. And so because fat is this rich, dense matrix, there's a lot of places for that energy to go. Whereas water, you've got individual H2O molecules, they're more dispersed, less tightly packed, and so that energy dispersion or energy transfer occurs more slowly. And that's why these recovery and decay times are slower for water, in a nutshell. And critically, this is where the contrast in a structural MRI image comes from. And by contrast, I mean the fact that you can tell there's, if you've got sort of a slice of the brain and the head, you can tell where the skull is and where the brain is and where the gray matter is versus the white matter versus the CSF. That's contrast, because some parts are dark and some parts are bright, some parts are gray. And really, if you think about it, the gray matter is mostly cell bodies in the brain. White matter is mostly fat because it's axons that are coated in myelin sheath, that's fat. So you get a really strong contrast in the brain from that sort of gray matter. White matter, CSF is essentially water with other stuff in it, so it's very watery even compared to gray matter. So you get this big contrast. So the whole goal of designing an MRI pulse sequence for structural MRI, we'll come to fMRI next week, is to maximize the contrast between those two tissues. And so what this is telling us is, okay, time zero here is when we turn that RF coil or that RF pulse off. So we send in some energy, we turn it off, these things start happening. We want to record the signal, so we don't record from that receiver coil all the time. We sort of choose a particular point in time where we take a snapshot of the signal at that receiver coil. And what we want to do is time that not right away, because their fat and water have, they're sort of maximally energized, but at some point where they're both starting to recover, but the difference between them is maximal. So if you don't wait long enough, you get a very small difference, so very little contrast. If you wait too long, then the water is mostly recovered as well, and so these lines are going to be close together, so you don't get much contrast. So you want to find that sweet spot where you can maximize the contrast between the fat and the water, and then you're going to get the biggest difference. So if I took the readout out here, what I'd see in my brain is that it would be really hard to tell where the white matter separates from the gray matter, or even where the ventricles and the CSF are from the rest of the brain. It'd just be sort of a fuzzy gray image. So as we maximize that contrast, that's where we get really sharp, crisp delineation between gray matter, white matter, CSF. And even like in a good structural MRI image, as you zoom in, you can see even within that sort of contrast within the white matter and within the gray matter, just depending on the density of stuff that's in there. And basically the same thing for T2 here is you want to find the decay time where you're maximally separating the fat and the water signals. And that all comes from smart physicists who know how to actually do the math to calculate these curves and so on. All right. And this is just another figure that's basically illustrating the same thing and sort of breaking it down more. And repetition never hurts. So again, here we've got this representation where the longitudinal plane, B0, that's the bore of the scanner, the stand-in magnetic field, is pointing up. Then our transverse plane's pointing sideways. So at the start, before we've done any RF excitation, all the fat and the water protons are lined up, more or less, with B0. And so you see the blue-yellow arrow there. Then we send in our RF pulse. We do a 90-degree RF pulse, meaning we send in enough energy to flip everything into the transverse plane. So now everything's nicely phase-locked and precessing in the transverse plane where our receiver coil can pick it up. We don't read out from that receiver coil yet, though. We allow a bit of relaxation to occur. And so you can see here the fat net magnetization vector is recovering faster, and the water one's recovering slower. And that creates some difference between them. Now, in actual practice, when we're doing MRI scanning, we don't just sort of do one RF pulse, read out, and we're done. We're sending in a whole series of RF pulses, and we're timing them in such a way that after the first 2 or 3 pulses, we kind of achieve this steady state where you flip it, it recovers a bit, and then the next pulse flips it back exactly into that 90-degree plane, recovers a bit, flips it back, and so it's constantly sort of doing this sort of thing. Or you can actually, because they're additive, you don't recover that all the way, so the effect is that your net magnetization, that word is really hard to say, net magnetization vector goes past your transverse plane and then recovers back into the transverse plane. And because we're reading in the transverse plane, what really matters, and you can kind of, those gray lines aren't super crisp, I realize, but what you get is that now here's the vector for fat, and basically if you go from where that's pointing down, draw a straight line up to the transverse plane, that's the amount of signal we're going to record from water in the receiver coil, because the receiver coil is sensitive to what's exactly in the transverse plane. And similarly for fat, you get this projection up into the transverse plane. And so this is telling us that at this point in time, you're going to have a strong signal from fat and a relatively weak signal from water, just because of where their vectors sort of hit that transverse plane. And that becomes the basis for your image, which then looks something like this. And so you can get different images. Actually, let me step back. So the one thing that I haven't mentioned yet is, so I'm saying you send in RF pulse, let it recover a bit, send in another one. There's a critical parameter called the echo time, and that's how long after the RF pulse do you actually read out from that receive coil and get your signal. And so it's your echo time that's basically being determined by that green line, that T1 contrast there, or your T2 contrast. So your echo time is when you want to read out from that. So you set your echo time to a certain thing. And critically, you can get different contrast weightings, which we call T1 or T2, depending on various scan parameters, including what you choose that echo time to be. So if you look here, that green line for maximal T1 contrast is occurring just before 1,000 milliseconds, so just under 1 second after the RF pulse. The T2 decay curve, T2 recovery times are quite different, or decay times, sorry. And so your echo time there for maximal contrast is more like maybe 300 milliseconds, something like that. So depending on whether you read out at, say, 900 or 300 milliseconds, your image is going to be more dominated by the T1 contrast or by the T2 contrast. And you can see that critically here, the yellow line is above the blue in T1 recovery, and the blue line is above the yellow in T2 decay. And so the T1 and T2 contrast weightings result in different images. So the T1 is the one that I've been describing so far, and that's sort of the typical anatomical image that you'll see from MRI, where white matter is bright, so fat is bright, water is dark, so CSF is dark, right? And that lines up with fat, the yellow curve being the sort of higher one here. So in T1 contrast, we're sort of maximizing, we get the biggest or the brightest signal from fat and the darkest signal from water. In a T2 weighted image, it's the opposite, so water actually gives us the brightest signal. So here you can see there's all sorts of white in the ventricles, in the middle of the brain, all around sort of the outside of the brain and inside all the sulci. So that's the cerebrospinal fluid that the brain's floating in, and that's giving you the brightest signal because we're getting the brightest signal from water. And then white matter is actually going to be dark on these images because it's fat, and we're getting the weakest signal from fat, and then the gray matter again is sort of gray in the middle. In typical functional cognitive neuroscience imaging, T1 weighted images are quite common because we want a nice looking structural image of our individual's brain. And then the fMRI images aren't using either of these. It's another contrast we'll talk about later. The T2 weighted images are not used a lot certainly not in functional imaging, and not a lot even in most cognitive neuroscience structural imaging. They are used quite a bit clinically because having these different weightings can show you different things. So if you imagine, say, multiple sclerosis involves white matter plaques where the white matter, the myelin, starts to decay. And so you can imagine that in a T1 weighted image, what would you see as a symptom of MS, do you think?
Less intact white matter?
Right. So you'd see, in terms of the contrast, you'd see like black spots or something inside what would normally be the white matter. And so you might see that, but there's actually a few reasons why you might see dark spots in white matter, including just blood vessels going through there, because blood is more watery, and so those can cause little black spots, which caused me a lot of the concern the first time I saw a structural image with my own brain. It was fine. But if you also have a T1 weighted image, then that'll help because you've got different weightings, and now the white matter holes or the plaques should appear brighter in that one. Other ones, like for diagnosing stroke, if somebody's got an ischemic stroke, so they're bleeding into the brain, then you've got more blood in a particular area, so that's more watery, and so that'll show up differently. And so for clinical diagnosis, having T1 and T2 contrast both can help a radiologist make a differential diagnosis and sort of triangulate from. And there's actually other kinds of contrast weightings as well. T1 and T2 are sort of the simplest and most illustrative for talking about MRI physics. But in typical clinical protocols, they'll do a number of different scans with different kinds of contrast weighting, so that that are typically done around the particular diagnosis they're looking for, the different things they think might be wrong with the person. All right, so that gives you your T1 and your T2 weighted images. And that's basically how we get an image. What we haven't talked about yet is how you get a 2D or 3D image. All we've talked about so far is you send RF pulses in, and you record some energy, and as I showed you, the receiver coil signal is just like an oscillating sine wave. It's not a brain. So there's obviously more that we have to do.